Hey, this is Dr. B, and this time let's talk about oxidation number. Keeping track of charges is easy when you're dealing with ionic compounds. You just have the charges that are there. Even if it's forming an oxide from an uncharged atom, it's not so hard to keep track of the charges. We know the charges of the atoms are 0. We know the charges of the ions from the periodic table. We're good to go. But when you do organic chemical reactions, it doesn't appear that anything is charged to begin with, and yet there is a flow of electrons occurring. And for that, scientists have come up with oxidation number. It's a bit of an artificial construct. It sort of treats those atoms in an organic substance as if they were ions. So our definition of oxidation number is the charge an atom would have if it were an ion. Is it the same as charge? It is the same as charge if it had a charge, but it doesn't really, right? So carbon dioxide does not have any oxides in it, for example. If it were magnesium oxide, it does. Those are ionic compounds with real negative charges. It treats the atoms as though they are ions just to help with the bookkeeping. Free elements, like you might expect, don't have an oxidation number. They're just like atoms, so their oxidation number is 0. And if they're just single element molecules that share those electrons evenly, end of story, no charge. So let's apply that. Which of these atoms below have an oxidation number of 0? Well, here's what I think. You can do this on your own. +1, -1. Oop, that's alone, so that one does. Right? And here's an example, by the way, of lots of atoms and molecules that have no charge, 0. But these ones, +1, -1, this one does. This one does because it's just a diatomic molecule. This +2, -2, so no. Yep, diatomic molecule. No, these are different, right? So no. N2, diatomic molecule, Cl- has a -1 charge, so those are the ones that have an oxidation number of 0. In monatomic ions, just use the plain old charge, and it might be given, right? So lithium plus is +1. Fe3 plus clearly has a charge of +3. O2 minus has a charge of -2. That would also be its oxidation number, because it's as if it were an ion. Well, it is an ion. The rule for oxygen is a little bit funny because there's a couple different flavors of it. Usually oxides are -2, but beware of the peroxide anion. It's O2, and it has a -2 charge. Therefore, each oxygen is -1. This becomes important when you try to balance some chemical equations, so just be aware of that. Hydrogen also comes in a few different flavors. If it's H2, I'd say 0, but if it's an ion, it's usually +1, right? Hydrogen chloride, +1, -1. But since 2 valence electrons constitute stability for hydrogen, right? It would be isoelectronic with the noble gas helium. You can also get a hydride. It can gain one. And they always put it at the end like that. So when you see it at the end, what's the charge on that? Hydrogen, -1. What's its name? Lithium hydride. So that one gained an extra electron. Much more unstable, much more rare, but it does exist. For group 1 and 2 ions in fluorine, you can probably guess what will happen. They will have the +1 for the group 1s, no variety there. +2 for the +2 alkaline earth metals, and fluorine small enough that it only has been observed to be a -1 ion. So +1, +2, and -1. And don't forget that the total oxidation number, when you're working the whole thing out, has to equal the charge on that substance. When we do examples, that'll be pretty clear. But if you have the carbonate dianion, CO3 2-, when you add things up, you better get -2. Let's go ahead and do some examples. Find the oxidation state of each of carbon in the acetate ion. Well, let's do the charge of everything, right? That's the acetate ion right there. What do we know? It's not a peroxide, so each one of those is -2. That's -4. This is a hydrogen with a +1 charge because it's not a hydride. So we are at -4 +3. That's -1. And the overall charge of the thing is -1. So I don't think those carbons have any charge at all. The oxidation state, oxidation number of carbon is 0. Now, usually you'll get whole numbers when you do the math, but tell me the charge, the oxidation state, I should say, of iron in Fe3O4. Well, here's how I would do it. Maybe you could do this on your own. Oxides -2, so we've totaled -8. When we're done, we're supposed to have 0, so oh boy, 2 is too small, 3 is too big. I think it's going to be 8/3, right? 3 times a number minus the 8 is going to equal 0. That sets it up nicely. X equals 8/3. So that's how you do it mathematically. Okay, do you have this down? Check it. Find the oxidation state of each atom or ion. That's an atom, so 0. Whoops, where are we? Blah, 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 blah. Okay. Calcium atom has to be 0. Calcium cation +2, fluorides are each -1. Calcium oxide, calcium's +2, it's alkaline earth. The oxygen group, they're -2, that offsets nicely. Calcium hydride, so +2, and each hydrogen is -1. SO2, that's -4 total there. I guess sulfur is +4, so what is the charge on sulfur? +4, each oxide is -2. A little different here. We're at -4, but once we add on the sulfur, we're still supposed to be -1, so I better make sulfur a little bit lower, +3. Here's my math. +3 -4 equals -1. SO4 with a 2- charge. You know, anytime you go below the second row, you start entering the area where there's available d shells, and d orbitals, I should say, and therefore they become polyvalent. Sulfur here, let's see, we are at -8, but it's got to be -2 when we're done, so I better make sulfur +6. Here, dichromate, -14 plus half of whatever that is, plus that doubled, I should say, will still be -2, so we better go only to +12. That means chromium is 6. Did you follow that? 6 times 2 is 12, but 7 times -2 is -14. That will make it -2, so I get 6 and -2. Sulfuric acid, well, H is H+. Sulfur, well, I don't know yet. It's polyvalent, but that oxide is not, so +2, -8. We are at -6 to offset it. The sulfur better be +6. And S8, it doesn't matter how many of those. It is just a diatomic, or really a polyatomic molecule, therefore 0. This is an introduction to oxidation numbers.